All right, let's take a look at our first distillation problem. It'll be a flash distillation problem. So flipping over to the problem statement, we're going to look at using a flash drum to separate methanol and water. Okay, so let's start by just getting this set up. And so I'm going to start by changing my engineering units. So I'm going to put in common SI and change from kilograms to kilomole. And then for our components, we have methanol and water. Okay, great. So I'll recommend this NRTL model. Okay, so that is great. So I'm going to keep it as is. All right, so then in terms of a flash drum, okay, I'm scrolling down in my unit ops. And here I have a flash drum. Okay, so when I look at my flash drum, I can have multiple input streams. It's tendency, I guess my habit is when I have multiple inlet streams, I tend to send them to a mixer and then send it as an inlet just so I know exactly the composition of what's going into my column. But you could have multiple inlet streams. Then you have 3 exit streams. So if I just have a vapor liquid separation process like I have here, then I'm just going to use my top and my bottom. Where this third output comes in is this is going to be the same unit I would use for to model an extractor. And so this is for the case of vapor liquid liquid equilibrium. So I would have 2 vapor streams and then I would have a liquid stream. Okay, but we'll tackle that in another problem. So for this problem though, I'm going to have a single feed. Okay, the feed can go to any one of these blue input nodes. I'm going to have 2 product streams, so I'm going to drag those 2 in. And in terms of my input stream, I believe it was 55% methanol and 45% water. So I'm going to convert this to mole, get in mole percents. So I'm going to make this 55 and 45. Then I need my total flow rate. My total flow rate is 100 kilomoles per hour. Temperature is 75 degrees C. Wait, no, the drum temperature is 75 degrees C. It's 3 bars and a saturated liquid. Okay, so how I do that is I don't specify anything up here for temperature, but my pressure, I specify it's at 3 bars. Vapor fraction, I specify a value of 0, so it shows I've specified pressure and vapor fraction, so those both are green. So if I flash, it'll calculate the corresponding saturation temperature. So here we go. So vapor fraction is 0, means I'm indicating a saturated liquid. So by specifying a vapor fraction between 0 and 1, I'm specifying that I'm at saturation, or I have a 2-phase mixture. 0 just means saturated liquid. 1 would be saturated vapor, and a value in between would be 2-phase. All right, so now in terms of the drum, so there's various operating modes. Okay, so when I look at the problem statement, we're told that the drum's going to operate at 75 degrees C, so that corresponds to specifying temperature. Then they have various V over F values. Okay, and so we'll see how we can play with that. And so the operating mode is going to be this one, number 4, right? So 4 specify V over F and T. Okay, so mole vapor fraction, so this is the fraction vaporized. Told that the fraction vaporized, we're going to try a different couple values. Okay, but I'm going to start with 0.2, and then my temperature was 75 degrees C. Okay. So if I do that, and then I run, it runs. So stream 2, that's going to be my vapor phase coming off the top, right? Vapor fraction of 1. Okay, right now it's in kilomoles per hour, but I can make that mole percent. So remember my inlet stream was 55% methanol, 45% water. Right, methanol is my most volatile component. So I have a vapor stream which is rich with respect to methanol. Then a liquid stream, I'm going to make this mole percent, which is rich with respect to water, right? The inlet stream was 45% water. This stream is 50% water, just like my inlet stream was 55% methanol. And coming out the top, it's 78.4% methanol. Okay, cool, right? And so you can pull all that information from there if you'd like. I'm going to look at the column right after it performs the calculation. It's going to calculate the heat duty, so that's going to be so it's positive, so it's the rate at which heat needs to be added to my drum to dry myself to that two-phase coexistence. Okay. But yeah, I guess I'll also point out, so when I look at my pressure, so my exit stream's at 75 degrees C, my drum's operating at 75 degrees C. I specified the fraction vaporized and the temperature. I didn't specify the pressure, right? And we see the pressure is actually reduced to 1.1 bar. Okay. So we start at a higher temperature and a lower pressure, or higher temperature, higher pressure, and we're reducing the pressure, and then the temperature is also decreasing to bring myself into two-phase coexistence at 75 degrees C, such that my vapor phase is 0.2, or 20% of my feed is vaporized. Okay. Cool. All right, now just to kind of play around a little bit, is it also asks, so that's 0.2 or 20% vaporized, but it also says, what about 40, 60, and 80? Okay, and it says, calculate the feed temperature. Well, that's going to be fixed regardless. Q, the heat duty, the flash drum, and for the drum, P, Y, X, V, and L. Okay, now, what it means by this is okay. Here's Q, the calculated heat duty. Okay. But then Y would be, say, the mole frac of my most volatile component, right, coming off the top of my vapor. Okay, X would be the mole frac of my most volatile component coming out the bottom of my liquid. And then this would be, 80, that's my flow rate of my liquid stream. And then this 20, right, that's going to be the flow rate of my vapor stream. Okay, cool. Now it asks for a range of values. So, let's see if we can get a sensitivity study to work. Right, and I'll cross my fingers and hope it works. But if I want to try, okay, what I'm going to check on is, remember V over F, that's my first variable here. Okay, so I'm going to try adding a sensitivity study. I'll call it frac vape, so fraction vaporized. Okay, and I'll say, well, what I want to change is equipment 1. Okay, I want to change parameter 1, and what's the parameter? It's V over F. Okay, so there's no component I need to specify. There's no units. Okay, and I'm going to vary this from, I'm going to go from 0.2 to 0.8, and I'm just going to say, hey, let's do 10 steps, or let me do 11 steps. Okay, great. And what do I want to record? Well, what we were looking for is it asks us to look at Q. So for equipment 1, I want the calculated heat duty, so that's number 5. Okay, and no component, variable unit. Well, what should the unit be? It's a rate of work or rate of energy. So let me check work. Okay, dependent variable 2. Well, in stream 2, I want to track the component mole fraction of methanol, and that's dimensionless. I also want to track in stream 3 the mole fraction of methanol, which is dimensionless. Then they also asked, so go to recording stream from stream 2, we want the total molar rate. Total mole rate, that's a unit of mole rate, and that's going to be V. And then for stream 3, I want the total mole rate, and that's going to be L. I'm going to click OK. I'm going to run it, and I'm going to cross my fingers. So recording variable 1, label not specified. Okay, so let me see what it doesn't like. So I'm adjusting V over F, recording variable 1. Oh, it says I didn't give a name, so that's Q. I'm going to call this Y, and this was X. Alright, let's try now. I forgot to give the variables names. So if I click and I run selected, okay, it runs, it's done. I'm going to plot my results. So here's the fraction vaporized. We can look at the heat duty. Okay, so as the fraction vaporized increases, the heat duty increases, and so that's in megajoules per hour, just as I would expect. And let's also look, and so let me do Y and X. Pretty sure when I check 2, they open up on one graph, but let's do fraction vaporized. The fraction vaporized increases, Y decreases, as I would expect, right? I'm producing, getting more vapor coming out the top, but the concentration of my most volatile component is decreasing. If I were to look at X, okay, this is with respect to methanol, remember. Okay, so with respect to methanol, so let's see, does this make sense? So it's starts out, it's in value close to 0.49, and then it decreases. So it's becoming more pure with respect to water. If I look at, well, V and L are just going to increase linearly, so it's not too exciting, but amount of vapor goes up and then amount of liquid go up. But there you go. So we're able to perform a sensitivity study, and all is great. Okay. So, A just makes a comment on keeping track of association. And just, what that is if I go back to my home tab and I look at my thermodynamic settings, so it uses this NRTL model. Okay. So here's a selection if I have something like a carboxylic acid and I want to keep track of vapor phase association, that's there. Okay, but what this is referring to is in this box here, is we can actually use an equation of state to calculate the fugacity coefficient to use in our phase equilibrium relation. So by default, it's turned off. We typically assume it's negligible, right, in our thermal class, but we could compute it. And so if I just click correct using SRK, it'll use the SRK equation of state to calculate the fugacity coefficient for the calculation. My theory would be by default it's turned off because typically we assume it's negligible. But if I'm asking CHEMCAD, so CHEMCAD's already numerically solving my mass, energy, and phase equilibrium balance. Well, now you're just asking it to make that phase equilibrium calculation even more complicated by computing a fugacity coefficient using an equation of state. Okay. But if I click OK, that'll all be the same. And so, let me just click on it now. So this should still be from the case of 0.2, fraction vaporized at 0.2. Right, at 15.69 kilomoles per hour of methanol coming out in the vapor. So if I run now with SRK to count for vapor phase non-idealities, right, you really don't see much of a difference. Okay, and that's just, it's just it doesn't make a significant difference for this system at 1 bar. Okay. All right, then the last kind of point you make is just looking at how we can generate phase diagrams. Okay, and how we can generate phase diagrams, TXY or PXY, is I'm going to come over here so I'm on the Home tab. I'm going to come over to Charts, and then I can generate TXY. Okay, so it's listed TPXY. I could generate a TXY or PXY. So my first component's methanol, second component's water. Okay, you can choose how many points you want, right? So by default it's 20. You can add a third component that's useful if I'm trying to look at the effect of an entrainer. Okay. And then we have a mode. So right now it's going to generate a TXY. at a pressure of 1.01325 bars. All right, so essentially that's 1 atm. It's going to type in 1 bar, and then this estimate temperature. It's just so I'm generating a TXY at this pressure. The temperature will just be the initial temperature it starts with as a seed as it performs the calculation to solve for temperature along with composition. All right. So we'll play with this. Well, we'll play with. Let me look at this in a second. This is the model that's in my that's currently checked in my thermodynamic settings, and we'll see how we can modify that in a second. Now over here on the right, we can control what's outputted. So by default, this can make a picture, but if I want to generate tabulated data as well, I can check generate report. I'll keep it in mole fracs. We'll use actual compositions, compared to normalized compositions, and that'd be useful if I were to add a third component. And then you can control what you want to output. So right now it's a XY diagram and a TXY. Okay. And if I click OK, I get a TXY, I get a McCabe-Thiele, and I get tabulated data. Okay. And actually this is interesting. So since we had SRK checked to calculate fugacity coefficient, so when I look at our tabulated data, right at 1 bar, right, these last 2 columns are the computed fugacity coefficients, right, and they're between essentially 0.98 and 0.99, so they're pretty close to 1, which is why the effect on our result is pretty minor. Okay, and you get a nice little report. It computes everything for you, then even reports the BIPs used by NRTL. Okay, pretty cool. Okay, but again, this last row. So if I were to come back over here. So I'm going to come back to my thermodynamic settings, and if I say no correction, what will happen is when I generate my TXY and do exactly the same calculation, okay, so when I look at the tabulated data, you'll see the computed fugacity coefficient's 1, right? So by no correction, I'm not calculating the fugacity coefficient using the equation of state. So it's just going to use a value of 1. Okay, and that's what we see here. All right, last thing I want to show you on that related to that question, I'm going to actually let me close up a bunch of these. I have a bunch of tabs. Is within that generate phase diagrams, we can play around with comparing models. Okay, and so for my main tab, when I generate TXY, I still have vapor phase association turned off. Okay? And by default here, we see NRTL, which is the excess Gibbs free energy model that the CHEMCAD's recommending, which is the box I've checked in my thermodynamic settings. But if I click add row, right, I can see I should be able to click then on NRTL and go to a drop down, and I could say, okay, let's look at Wilson's equation, or let's look at Wilson. We can add another row, and I could say let's look at the use of UNIFAC, right? You could try anything, right? Or I could try Rail's law, right? I could try Rail's law. I could try a predictive method like UNIFAC. Yeah, it's actually for Wilson. Instead of Wilson, let me have more fun, and let's do that's Rail's law. We can use the SRK equation of state, right? That'd be a fun one. Let's try NRTL SRK equation of state in UNIFAC. Okay, so now when I plot them, right, I'm going to get plots in which I compare all the results. So this is a TXY. Okay, cool. And so NRTL is what was recommended, and so NRTL is the blue. It says it's the blue and the red, but am I missing something? So I'm going to come over to the McCabe-Thiele one, and so blue, okay. So the blue and green pretty much overlap, and so the blue is NRTL, the green is UNIFAC, and then the red is use of the SRK equation of state. And so if I try and look at the data here, I wonder if it's just a matter of how the data is presented. Well, I should have gone back because it shows blue and red being NRTL, which is this. SRK is green and purple. Green and purple. Okay. And then UDFAC is yellow and blue. Oh, I see. It's because I have two different blues. So NRTL is red circles and blue circles. UNIFAC is yellow squares and blue squares. So they pretty much overlap with each other again. But SRK, equation of state, gives some, madness. Okay. Cool. And then, you even get tabulated data for all the different methods which you could compare. Okay. And so it's just under, charts, TXY, you can choose and select different models. Okay. Cool. And so under phase option here, there's a drop down vapor, liquid, liquid, solid. So this would be cases for systems that could form a minimum boiling heterogeneous azeotrope. So if I have two components that are partially miscible, then I need this option to make sure I'm properly modeling our phase equilibria for those cases. Why isn't it checked by default? Well, it becomes a much harder calculation because then I'm going to assume that I have a vapor and two liquid phases that could be in equilibrium beyond just a single vapor and liquid phase. But yeah, so that is, let's generate another one. So that is this part B, in which you could use this to compare excess Gibbs free energy models as well for when you perform your calculations. And so clearly the UNIFAC and NRTL, the phase diagrams were in pretty close agreement, so wouldn't expect a significant difference when modeling, say, a flash drum. But SRK was drastically different, so we'd expect a pretty big difference there. Okay. Last comment again is, how does CHEMCAD select these models when it makes recommendations? Is remember when I'm using our popular, excess Gibbs free energy models, UNIQUAC, NRTL, Wilson's equation, is what's going to happen is there's some internal database of experimental data that CHEMCAD's using to regress those parameters to. And so, which model's the best model for the system is, well, which one does the best job fitting that data, and so that's how you determine the best model. UDFAC is predictive, but so when it recommends NRTL for that system, NRTL typically performs best for water, but it's based on the internal data used to regress parameters for that binary system. NRTL is the one that did the best job. So I hope that helps. If you have any questions, let me know.